Hello, everyone, and welcome back to HDL for Digital System Design. I'm Dr. Mike Brofchek. It is great to have you all here with me. So we're going to dive into the next major topic for this video series, which is sequential logic fundamentals. And to do that, we need to talk about what drives sequential logic, and that is the ability to store information into registers. And that storage happens at a very regular rate using clocks and edges. So let's get right into it. So where does this live? Well, every single device that you have, every piece of electronic equipment, every digital chip around since the 1970s runs on clocks. It is what enables us to do work, snapshot it, and continue doing more complicated things. And we do that at a very high rate of speed. So consider that your phone has a system on chip that has over 50 different clock domains running at different frequencies, from 32 kilohertz all the way to 3 gigahertz, again, depending on your system, depending on your actual SoC. The whole concept of clock distribution within a design is an entire specialty. There are designers that do nothing but focus on the clock, from phase lock loops to clock trees to the skew analysis. How these clocks work and interact with one another, how they're distributed, is a massive undertaking. So today is our first formal introduction to the idea, as well as the concept that governs all modern digital design, which is the register transfer level of abstraction. So within this course, everything from here on out uses a clock in some way or another, from counters to our debouncer to how we stimulate test benches to finite state machines. You will see it everywhere. So understanding how clocks work, getting the right mental model is going to be really important for the rest of this course. So something I should also mention, it is not like you really have a choice between using synchronous design or not. It is not like there's a lot of different ways to build out these digital systems. It is pretty much the dominating methodology. If you're going to build something, whether it's here, whether it's at a company, you are more than likely doing synchronous design. Asynchronous designs do exist, but it's really specialized. You do see it in when you are dealing with your reset conditions, when you have multiple clocks interacting with one another, or hardware that has multiple clocks and you somehow have to get things aligned. Um, Also, there are some global asynchronous, local synchronous systems, but by and large, you are going to be writing and dealing with synchronous designs. I will also mention that there are some niche designs and some research topic areas that do work on completely asynchronous spaces, but those are, again, far and few between. If you're doing something with dealing with digital logic design, it is more than likely going to be synchronous. So let's start off with a major misconception, and that is that your clock does not drive your code, right? You might want to think, oh, the clock is like a loop counter, and every time I see clock tick, that always block with that positive edge clock, it's going to run once, one statement at a time. And that's not at all how it works. Think of the clock more as a capture signal, an event in which we are going to capture the state of all the combinational logic um, throughout our system and capture it simultaneously. So in every rising edge, for what we're looking at, there are different models, but for every rising edge, every flip-flop is going to simultaneously snapshot its inputs and begin outputting that. So between edges, between those positive edges, our combinational logic is going to essentially be working on whatever input it sees, whatever is driving out of flip-flops into combinational logic, it's going to work on that. And then that output of all that combinational logic is being driven into another flip-flop that is going to capture, again, on this positive edge. So the code that you're going to do describes the structure, and the clock is just running and snapshotting into all of the registers. So way to think about this is if you were to take an always block that is sensitive to the positive edge of the clock, and you have 100 lines of code in there, it won't take 100 times longer to run than a one-line segment of code. It will take the exact same amount of time. It will take however fast your clock is running. All your flops capture in parallel. The length of your block affects the routing and the area, not the time that it takes. So that's a super critical thing to understand. So let's talk about the heartbeat of sequential logic, this clock a little bit more. We're going to look at positive edge triggered clocks in systems. That is something that, I mean, there are also negative edged clocked systems, but in this particular case, we're just going to look at positive edged ones. So what you'll notice is on that red positive edge, both of those registers light up. The moment that that positive edge hits is when we are going to capture whatever input is being passed in. So there are two registers there. There's the one on the left that has input D. We don't know the combinational logic before that. And then we have the one on the right that is taking the result of combinational logic that's happening right there in the middle. The moment that that positive edge hits, we snapshot whatever is being fed into those registers, and we then output it, right? So we then output whatever that input D is out to Q. What happens after that? What happens after that positive edge? So that's whole top edge of the clock, then the transition down, and that whole bottom edge of the clock. We're doing all the combinational logic that we can. We're basically fitting as much as we possibly can in there. And then basically the process continues. So we do all that combinational logic work. That becomes an output, right, from that, I'll say that combinational blob there. And that becomes the input that will get snapshotted again at the next positive edge of the clock. This repeats over and over again, again, at the rate of the clock. So what this is describing is the register transfer level of abstraction. It's the fundamental abstraction for synchronous designs. So what do we have available to us on the Go board? Well, we have a 25 megahertz clock. Basically, it's running off a crystal oscillator connected to pin 15. If you had an oscilloscope, you can buy some pretty relatively inexpensive ones on Amazon for like $20, $20 to $60. There are obviously more expensive ones that have finer granularity. Basically, again, you're going to get increased resolution, higher sampling rates. No need. The idea here is we have a 25 megahertz clock running on this Go board, and that comes out to about a 40 nanosecond period. Actually, exactly 40 nanoseconds. So the thing is, though, that if we're going to be using this clock and we're trying to interact and engage with it, that is way too fast for us to be able to visually respond to. Persistence of human vision is somewhere around 24 to 60 hertz. Anything outside of that range, and it becomes pretty difficult for us to recognize. So what do we need to do? Well, we need to divide that clock. We've got this super fast clock. We need to find ways to slow it down so that we can interact with our system in a meaningful way, whether that's through input or output. So the clock divider is kind of a hello world of sequential designs. So let's take a look. If we wanted to blink an LED at 1 hertz, right? Um, so what we need to do is we would need to count 25 million clock cycles between toggles. So basically, we would need to count to 25 million. And let's say that we started off at low. Let's say that we had an LED that was not on and we wanted it to blink. So it's going to be off for 25 million clock cycles, and then it's going to be on for 25 million clock cycles. Well, if I want to be able to do that, if I want to count to 25 million, I need a flip-flop. I need flip-flops, right? A register big enough to count to 25 million. And so I will need that count to happen on a clock edge. So let's look at this maybe instead of trying to do a division by 25 million. Let's say that I wanted to slow down my clock just by 4 units. Let's see if I can do that. Okay, so looking at some really basic code here, what we have, and let's make this a little bigger for you. We've decided to, instead of slowing this down to 1 blink per second, let's just try to divide our clock by 4 just for now, just as a sample. So what we're going to do is we're going to count 1, 2, 3, 4. Switch how we have our signal. 1, 2, 3, 4. Switch how we have our signal over and over again. So to do that, we need a space to count, a place to store what we're counting. So we have right here a 3-bit counter. Now to go to 4, we don't quite need 3 bits, obviously, but this gives us a little bit of extra room if we want. And then we need a space where we're going to hold our divided clock. So notice that it is 1 bit wide, and it's going to start off at 0. Our counter is also starting off at 0. What are we going to do? Well, every time we have the positive edge of the clock, we're going to first check, have we reached basically the value that we were trying to reach. So in this particular case, we wanted to count to 4. So 0, 1, 2, 3 gets us to 4. So if that's the case, we're going to reset our count, and we are going to then toggle the terminal. Basically, we're going to toggle that clock so that we can do that. And then we're going to end, and otherwise, right? So end else here, if we aren't saturated there, if we haven't hit our count, we're going to increment our counter. So we're literally counting by 1, and if we reach the value we were trying to get to, we're going to reset our counter and flip our clock signal. Outside of this, outside of the positive edge, at all times, we're going to have some output, right, being driven by our signal that we are, our clock divider. We're going to output this. Now, why are we doing this? Well, this output doesn't necessarily need to be a clock signal. It could be an LED. It could be anything that we want to assign at this slower rate. So what does this look like? Well, what this looks like is we have our input clock here running at some rate, some frequency, and we're going to start counting, right? We count essentially at the positive edge of this clock here at iClock, and we get 0, right? That's where it starts, right? So imagine that we just start at 0, and at every subsequent positive edge, we are incrementing by 1. So you see 0, 1, 2, 3. So that basically equates this logic here, right? In terms of we are counting by 1, right? And if we hit 3, right? So if it ends up being 3, what do we do? Well, we set count back to 0, and we flip the state of our clock divider. And our output side here is basically just output clock divider is equal to the register clock divider. So the output clock division here basically is low, toggles high, count 1, 2, 3, toggles again, and the pattern continues. So this is just very quick demonstration of dividing a clock by a certain amount. Here I've counted to 4, but you could easily count to 25 million. And that's actually what we're going to do next. So let's take a look real quick at a live demo where we do an LED on for a second, off for a second. So this is going to be located in our lecture examples, week 1, day 4. And we're going to look at sample 1, example 4 within that space. And we'll make a simulation, and we'll also get that output on our Go board just to see what that looks like. All right, so let's take a quick look. And what we should see here is the terminal. And in the terminal here, what we have going on, let's double check that we can get there. So we're going to go to the lectures. We're going to week 1, day 4. You can take a quick peek inside. You'll see we have a handful of examples. So we're going to look at the sample 1 here and see what we have. So we have the first file is day 4, example 3, LED blink rates. The other one is a test bench that we could simulate with. But for now, let's just take a peek at what we have. So you can see in the description here, LED blinks 1 second on, 1 second off from this shared 25 megahertz clock. Toggle once every second. So the full on-off period is 2 seconds. All the other LEDs are purposely tied off to off. So if you want to go take this code and extend it, you are more than welcome to. So what do we have? Let's scroll through one line at a time here. Let's look at our inputs and outputs first. So input is the clock based off our crystal oscillator here, 25 megahertz. We are going to have an output wire to LED 1, and that's the one that we're going to want to toggle. And everything else, LED 2 and 3 and 4 are all tied off. And we will do that explicitly here just for the sake of doing it. All right, so first thing to note is we have a 25 megahertz clock, and we want our counter to roll over when we hit 25 million if we want a 1 megahertz clock. So note that we actually have to count, we start counting at 0, not 1. So what we actually want to count to is 24,999,999, right? So what we do is we store the clock frequency that we have, and we also are going to compute how far we want to count, which is essentially the frequency of the clock minus 1. And this is, again, just to get this to a 1 hertz clock, okay? So you have that number there. Why that number matters, we need to know, essentially, what size of a register we would need to capture that number. So what actually would work is 25 bits. 2 to the 25 is 33,554,432. That is the smallest sized that will actually fit our 24,999,999 value. So that is a bit of scoping that you would have to do. You can ask yourself why we aren't doing that computation internally here. Here it is. Here's our register, 24 down to 0. All right, so 25-bit counter called R count. And we are setting it, as you can see here, explicitly to 0. All right, so we're following that good behavior in that pattern of actually doing that. And we've done decimal 0 there, though others would have worked. All right, what else do we have? We have the value of our LED that we want to toggle. So let's have that in a register as well. And we're going to start that off single bit and value of 0. Now, what are we going to do with those two registers? Well, we're going to follow a very similar pattern to what you already saw before. First, if R count equal T, right, or the one that we've stored here, all 25 bits. So this statement right here is our quality check, right? We have a counter here that's a register and some integer that we have here. And we're going to basically check to say, hey, are these equal? If they are equal, reset my counter and flip the value of the register that has LED. So it will be 0 first and then 1. 25 million clock cycles later, it will be 0 again. And that pattern will continue. Now, if we haven't hit this, if we haven't hit 25 million clock cycles, what are we doing? Well, we are incrementing by 1, right? And so because we start at 0, right, 0 to 24,999,999 is our 25 million, right? So we are going to count 25 million times, and that's it. That's all we're going to do inside of our always block that looks at the positive edge of the clock. We're going to do this over and over and over again, right, for all time. Now, at some point, right, we have not connected this R right here, this register LED, we have not connected it to our output. We're going to do that external to our always block. Here's that assignment. Here's the assignment that we care about. We assign output LED 1 to the value of register LED. Everything else is forced to 0 at all times. That's our module. So let's see what we can do here. We have a handful of options. We can do a make simulation, right? You can see that we have some things in our test bench that essentially this test bench is not really that great in the sense that it doesn't go long enough for us to see a lot of things, which is why I'm not showing it, but it does at least simulate the design. We have an ability to look at what is produced and made, and what we see here is we have some carry, and we have a D flip-flop, and we also have other D flip-flops here, and some LUTs. So essentially, what we have here is a large majority to hold on to the value itself. All those bits that we need to compute is basically what we have here. So, all right, this should fit comfortably on our board. So let's change our view real quick to see our board. We don't really need our terminal at the top there or our VS Code, but that's okay. It's there anyways. Um, Actually, maybe what we can do is show you the output. Let's see if it generated any waveforms. I don't think we did, but let's just double check to see. Um, so if we go to our lecture examples, day 4, example 4, looks like we do have a VCD file. So if we click on that, we'll actually get, real quick, let's see, we can actually add this in here. So just showing you that we have that ability to view our waveforms within this space. Now, I mentioned that this wasn't a complete test bench. We don't simulate nearly long enough to see the output change. So that's basically why I wasn't really showing this off, but it is possible to view VCD files, the output waveform files, directly within within our VS Code instead of using GTK Wave that we've been using for other parts of the class so far. So with that, what we really wanted to see is down here on the Go board. I've not done the make program yet, so let's do that. And so when we do make program, what we expect to see is we expect to see LED1, which is labeled right here. We expect to see that blinking at a rate of once per second, an on of 1, off of 1 second. Um, so let's just see if that roughly matches what we expect. I'm not in the right directory, so that's not going to work well. It looks like we got exited out of where we wanted to be. So 1 second here. This will actually be a good time to review what we need to do anytime we are starting off things in our space. Notice that we are using Nix to get all of our tool chains up and running appropriately. So Nix develop anytime you're at the top level of the directory. And what we should see is all of the tools getting loaded up here. We now should have access to everything we want. And let's go back to lecture examples. We are in week 1, day 4. And again, within here, the day 4 S1 example 4. And so again, we have all the things here, and I should be able to do a make program. Um, so I'm going to do that, and get some warnings, which are okay. But what we now have is D1 here, blinking at a rate on off of 1 second each. What we can do real quick, just for purposes of this demo, why don't we go into our VS Code here, since we have the editor up, and you might as well see it here. So we have all of our code here. This is exactly what we had. This is our test bench. What I wanted to actually open was, here we go, the actual code. What would we do if we wanted to have this blink at a different rate? Instead of once per second, if we wanted it to blink, let's say, let's do every 2 seconds, right? So if we wanted to do every 2 seconds, I'm going to create, just real quick, I'm going to duplicate my number of parameters, so I don't necessarily have to. There are other ways, and we're going to talk about it more in a few videos, but let's just do a very simplistic, I'm going to just copy paste this. Let's do half the frequency here, and I'm going to put uh, half here, um, just so we can keep things straight. All right, and this new number that we're counting to is, well, I've already figured it out. All right, and Let's just, I'm going to have a second count. Although again, I admit there is a more efficient way of doing this um, by reusing actually the counter we already have. Um, but we don't need the full space here uh, of 25 bits. Let's actually quickly figure that out. Um, so we need to fit 12,499,999 in a so we can do log base 2 of that. And so that is going to be, real quick, 23, 24 bits, but let's see. Um, so we can do, yeah, so it's still going to take, it's going to take 20, yeah, so it makes sense. Basically half this number is going to take one less bit of space. Again, it's actually the trick on how we would do this if we wanted to observe this behavior. Let's see, we'll see if we can get that actually done before this demo is over. So what we have here is we have count here for one of these here. I'm going to, again, this is not, we could actually, we could copy this whole thing if we wanted to, but really there's, um, well, we'll just do it this way. This is, again, this is not the recommended approach, but I'm just showing that you could do it. It looks like it's providing me this suggestion, which is perfect, which is what I wanted. Um, perfect. Okay. The autocomplete is getting much better on VS Code. So in any case, what we've done here is we have a second check here that is essentially going to be checking to see if we're matching our new count, incrementing our count, resetting it here, swapping our LED. You know what? Let's do one other thing. Let's start our second LED high. So we should see it high first. But let's see how this works. All right, so I have this new code. Well, let's go back and see if this will still, as we expect, if we can. Let's do a make, let's make sim, just make sure. All right, it's failing because all our LEDs are no longer staying off as they expect, which is okay. But let's make prog and see if we get now a frequency that is twice as fast as the other one. So now instead of a 1 second period, we have a half-second period. So you can ask yourself, how would I have done this if I wanted a longer period? And so I just have my have this, right? And we now have obviously a half-second period. If I wanted to go the other way, what would I do? Well, I would take this and I would go one more, right? So if I wanted to go beyond this, I could go 50 million. And same general idea here. So let's do, I did already half. So now I'm going to do exactly. So now, honestly, VS Code has figured out my pattern here. Now, it's not entirely smart enough to have figured out, right here's a bug that is just introduced. I'm trying to count to 50 million cycles, and it thinks I can do it in 25 bits, and that is absolutely not the case, right? 25 bits, I can represent up to 33 million. I cannot get to 50. So I do need to increase this, right? I need 26 bits across the board. Actually, what did it do? It messed up a lot of things along the way. So, right, so we need 26 and we need this to be 26. And let's see if it was smart enough to add in. It was not. So let's add in our new counter. It looks like, and now it's figured it out. And all right, so thank you VS Code for doing that. We now have this new version here that is going to see if we match um, our new value that we're looking for, which is 49,999,999 clock cycles. And let's see if we can get that to show up on LED 3 now. So let's do another make program. And so what we should see is the first LED blinking at a rate of once a second, the second LED blinking at a rate of once every half a second, and our final LED here doing every 2 seconds on, 2 seconds off. So there you go, just really quick. And this was, again, a very, I'll say not clean way of doing this. There's a lot better ways to do this, especially because I have 3 clocks that are all multiples of one another. I could just have one counter doing this. Again, we just actually need the third one, right? I claim that you can do this behavior with just this particular outer loop counting, and the checks could be slightly different here. And you could be much more efficient. You don't need all of this logic to accomplish this task. So I'll leave that as something for you to think about. And let's, for now, come right back to our presentation. So again, the original demo was 1 clock, 1 counter, and 1 terminal value. This LED, we could see it actually blink at human speed, right? It was slowed down far enough that we could see it. We used, again, the always block, and we are looking at the positive edge of the clock. And our pattern was essentially looking to see if the number of ticks we were trying to count was essentially our clock frequency that we cared about minus 1, right? Because we start counting at 0. There are ways that if you don't want to do that, you could start counting at 1 and store your value all the way up. That is reasonable as well. Not recommended, but you could if that helps you. We started off with all the other LEDs tied to 0, just so you could focus on the 1 clock. But we'll generalize this when we talk about segment 4. So let's talk about the fundamental pattern behind all of this. What we're going to do is we always have this always block, right, that looks at the positive edge of the clock. We start, we have an end, and we look at RQ, right, the output gets assigned the value of the input. So on the right-hand side, we have our input, RD, and it gets assigned to RQ. That's the general pattern. And what this creates is a D flip-flop, 1 bit of memory in this design. What this looks like on the design we have when we start doing this make stat is essentially a D flip-flop primitive. So what are the things we have to have? We need a positive edge clock in the sensitivity list. We need a write register on the left-hand side, right? Register is where things are being stored. We need to use this special assignment statement here, which we're going to talk more about in the next segment for the assignment. If you miss any of these things, you have not written a synchronous flip-flop. You've written something else. You've created some other hardware. So take a look at these 3 examples. Take a pause and tell me what you think is missing for each one of these. So is there anything missing? So tell me what you think is missing about these blocks. It is not the begin and end, right? These are single line statements, so it's not your begin and end. That would be good to have, but that's not what's missing. So is there anything missing from the first one? This always at positive clock, Q equals D. Then we have another one, always at clock, Q with our assignment to D, and then another one, always at wildcard Q assigned to D. Let me correct myself on that first one. I said Q equals D. I did mean Q is being assigned to D. That's not an equality check, but it is a different kind of assignment. So the answers. First off, number one works mechanically. It will synthesize, but it uses something called a blocking assignment, which is what we've actually been using throughout all the videos so far until today. So it's actually okay if you just are dealing with one thing, but it's actually catastrophic if you're doing other things. So don't ever write it like this. We have a whole video on this next time. Um, so number two, it looks at the clock, but it's looking at both edges. It looks at any changes. We have clock there, but we don't say positive edge. So you'll probably get some synthesis warnings. Behavior is going to be unpredictable in terms of what you're really looking for. Number three, combinational sensitivity with non-blocking. This is actually pointless and produces a latch. Again, this is not what you were expecting. There is no clock in this. It is essentially going to observe D. And yeah, so this is not at all what you want. All right, so take a moment, pause the video, try to predict the output waveform here. I've got this D that toggles at 10 megahertz, the clock is 25 megahertz. What is Q, the output, going to be? All right, so take a pause, try to draw it out, and unpause when you have what you think is an answer. All right, so here's what will happen. Q updates on each positive edge of the clock. So what happens is we capture at positive edges, what is the output? What is D? So D is the input to our flip-flop at a rising edge. So right now, the first rising edge, when D is high, is 1, 2, 3 clock segments in. We capture and we see D is high, and so we output Q as high. Right now, there's a slight lag here that should be here, but right now we're showing that as negligible. So we get that output high, so Q goes high, and it stays high, right, all the way until we get a positive clock edge, which is about 3 from the back here, where D is 0. It's not until the clock goes high and D is 0 that we then get an output of 0. So you'll notice that the width of these is different, right? The Q width of being high is different than the width of D, right? Because again, it matters where the clock positive edge happens. It's not a one-to-one mapping of D being high and Q being high at some delay. That's not how it works. It matters when the positive edge is seen and what the value of D is at the positive edge. Okay, so, all right. I should mention that if D changes really close to an edge, right, so very close to that rising edge, this becomes unpredictable. We're not 100% sure if we capture the value of D correctly. We could capture it while it's 0, while it's rising, or when it's already 1. And so that's called a metastability hazard, and it's something we'll cover more in a future topic. But just know that if your value of D, your input to your flip-flop, is changing very close to the point of capture, that is a problem. All right, so the big lesson takeaway here, clocked register only updates on the clock edge. The value it captures depends on whether the input was stable at that moment. So sampling an asynchronous input is dangerous. So you might consider what might be an asynchronous input. I'll give you a hint. You have at least 4 of them on your device. So we'll show you some ways to avoid and fix that. Okay. We have another live demo here. In this particular case, it is to look essentially at the outputs of flip-flop. So let's just take a very quick look to see how that works. All right, so let's look back at our terminal here, and let's clear this, and let's go back day 4, and this should be segment 3, example 2, I think is in here. let's do a make sim real quick. And because I think it looks nicer, let's go and look at our editor view just to see what that looks like. So if we come in here and open our D flip-flop and add it, what we have is we have a clock, right? And notice that we have, let's get rid of fails here. That's one of our um, elements that we've added in. All we really care about here is looking at clock, our D, and our Q, right? So D is our input, Q is our output. You'll notice first off that Q, the beginning of our segment here, is unknown, right? There is no known value of Q at the beginning of our simulation because it hasn't ever gotten to see or latched an input. So you notice we latch our first input here. Right here is our first one. So rising edge, what is the value of D? Well, it's 1. And so we latch in D and immediately we output Q as that value, so it's 1. You'll notice D goes down not too long after, right? So D goes down, but we've again not hit another positive edge of a clock, so we retain the value that we had, which was 1, all the way through until the next positive edge of the clock right here. Positive edge of the clock, we read, D is 0, so now we output 0 on Q. Shortly thereafter, D goes high. D is high here and here and here. We're still outputting 0 because we have not hit another positive edge of the clock. There it is, positive edge. We reach it, D is 1, output is 1, and we notice that D has held high quite a while here through multiple clock cycles and goes down right here, stays down, but will not drop. Let's move slightly over here. We stay high on Q all the way until the next clock cycle, right here at this very edge. Clock cycle, we have a positive edge. D is 0. Q also goes down to 0. Okay, so again, remember this is simulation and we have perfect transitions, no issues, but there are a lot of instances here where the D value is changing very close to the clock edge, right? And so that can cause some issues. Particularly, I'd say, oh, this one's actually okay. Most of these are okay. Yeah, so in general, these are okay, but they're close. It's happening very close, and nothing is rising right before. So in any case, just things to look out for. Make sure you understand how this works. Recognize that this is a single flip-flop, but you could do with multiple flip-flops as well. And actually, that's one of the examples in here is a 4-bit one, but we will take a look at that at a later time. Okay, so let's go back and wrap this up. What did our tool build? We actually built one flip-flop. We can actually see that if I go back to the terminal here and do a make stat. Let's do that. All right. Oh, this is showing actually the 4-bit version right here. Let's see if I can get us the 1-bit. All right, let's see if it's up here or not. And if not, I might have to. There we go. Here it is. So for our D flip-flop, we get, or for the single bit one, we get 1 D flip-flop, which is exactly what we expect. There's nothing else happening here. We're storing 1 value. The 4-bit version, which we'll see a little bit later on in our video series, we'll end up creating 4 of them along with a LUT. So in any case, that's great. That's what we wanted. We have built really our first flip-flop officially and seen it. So everything else that we've seen before today's video lectures synthesize 0D flip-flops. We now have one, which is awesome. It is really the first hardware primitive that can store information. It remembers. And it's the building block for every single sequential design that we have. So we have about 1,200 of these positive edge D flip-flops within our within our FPGA. 12,000 would be pretty impressive, and would cost a lot more for an FPGA. So we have 1,200 of them. It is the number of states ultimately that we can store um, within our design. So that is a pretty critical number for us. All right, so as with all the other things we've talked about, right? AI can exist and you might ask it questions, but here's some things that you should consider. So why don't you ask your favorite LLM in Verilog? Why does the always at positive edge clock Q assigned to D create a flip-flop, but always at wildcard sensitivity Q gets assigned D does not? So why does it create a flip-flop in some cases and not in others? So that's what you could ask it. Predict, what do you think it's going to say before? Well, the prediction could be, well, positive edge means edge triggered storage, which is a flop. And the at wildcard sensitivity is a level sensitive, right? It's no longer clock edge sensitive, it's level. It's the value of the signals, not the clock, which basically creates combinational or latch, right? So good, strong AI space should mention edge-triggered semantics. Weak one says because of the clock without telling you why. The sensitivity list is structural, right? It describes what kind of hardware will be built. So just make sure you take that away. So big takeaways for this particular segment. One, clock edges define when state changes, right? So we've used always at positive edge of the clock. Between the edges is where all the combinational logic is computed for the next value that we are going to get to store. Our Go board has a 25 megahertz clock. If we want to see things rendered nicely or in a way that we can see them and interact with them, we have to divide our clock in some mechanism, some way. All in all, what we're describing here is the register transfer level of abstraction, and it is used everywhere. So between edges, your combinational logic computes and settles. On the edges, your flop captures, and this just goes on and on and on forever. So with that, what we're going to talk about next time is something that we briefly talked about today, and that is non-blocking assignments. So we actually used it. It's this symbol that has the less than or equal to together. It is not a comparison, and it is not exactly, it's not like a traditional assignment, but we're going to talk about it. We'll see it with a handful of demos, and we'll see what happens when you mix them up and you don't use the right one. So essentially, if you use the blocking version, which is the equal sign by itself, what happens? So with that, until next time, build some cool stuff.